Okay, what I have here is the last one-third of the larger config that we're using in here. So this has that last gene on it. It actually has the gene before it also, that little short one. So this is just the sequence. Here are the two places where the ends are. And I'm not going to do the CGs. I know that generally this first part is that first gene that's not there, and I know that generally the regulatory region is right here. So a lot of the things I'm looking for are going to be in this region. Any further, and it's really too long for a gene, but probably here, these ends here might cause a problem because they might, the certain signals, polyadenylation or termination might be in here or something. But I'm going to look for this anyhow, and the first thing on the worksheet is to look for the CGs, so I've kind of done that for you. The second thing on the worksheet is to look for your start and stop codons, but that's only if you have the amino acid sequence, and we don't have the amino acid sequence. These genes have never been sequenced. So you go to number 3 and it says look for polyadenylation and termination. So how do you do that? Well, if you look on your worksheet, on that set of worksheets, it says look for 2 sequences. So here's what I'm going to do. I'm going to look for those 2 sequences. One I'm going to put in green, and that first sequence we look for is AAUAAA. Well, we're going to use T's here instead of A's, so we're going to go AATAAA. And we're going to find every one of those that's in this sequence. All right, so here is our first clue as to where these might be. Now, the directions in the sheet say there's another sequence that comes after this one. About 30 letters after this one should come a certain sequence that will tell you if this is a polyadenylation signal. Now, polyadenylation is what you do. You add the polyadenylation to a sequence to get it out of the nucleus. If you don't do the polyadenylation, then it doesn't leave the nucleus. It's the protein or whatever, the sequence, the mRNA, will stay in the nucleus. And it could have some function there, but most genes leave the nucleus and need the polyadenylation. So what's the other one to give us a clue about this polyadenylation, where it should be? Well, it happens to be, let's see, the sequence is GT. So, or it's actually used, but we're using T's, of course, because that's the way FASTAs work. GT. And we do search, and here we go. So what we were looking for is we're looking for the green one, followed by, not too far down, about 30 letters, followed by the green one. So let's just start looking for where this might be. So we're looking for a green one like this, but followed about 30 letters down, a red one. So you don't see anything like that right here. You gotta have it going the other way. But as we move down, assuming that our gene is in here somewhere, we're going to look for this further down than close, because realize you had the other gene and then you had this one. You have the regulatory region, maybe introns and exons, and you scroll down, and what we're looking for is a green followed by a red with 30 in between. So here's a green with a red right before it. We don't want that, plus we want space in there. So here, if we look, there's only one. If you look through all of these, there's only one that matches this description. It's right here. Here's a green, and it's in the right spot too, followed by, actually I counted it, I think it was 29 letters, followed by a GTT. So here we go. This one fits, and that would be a good candidate for our polyadenylation signal. Now let's make sure it covers all the other parameters. We got the basic 2. Is there any more proof that this is it? Well, other proof is that there are pyrimidines on either side of the red signal. Now pyrimidines are purines are, A and G, so pyrimidines would be T and C, so T's and C's. Well, the thing is, it doesn't meet that criteria. You should have T's and C's on either side of this, but that's not a strong requirement. And you wouldn't know that. That's why we're watching this video. So we want pyrimidines wise um, in there, but we don't have them. But that's not a strong requirement. The fact that this is 30 apart and this meets it and this meets it, those are strong requirements. So this is good. So there is no other option. There are none of them that are even close to this. If you scroll through here and were to look at this, that come anywhere close to it. So you would say that this is your best bet for a polyadenylation signal. Now the neat thing about finding a polyadenylation signal is you know that the termination signal comes after it. So you can take this sequence and maybe take a couple of lines here and begin just searching as you did before for hairpin loops, and hopefully you can find a hairpin loop like you did in the operons and in our previous assignments. You find a hairpin loop that comes not too long after this one, and that would be it. So this signal is to add the A's to it, and then you should get a hairpin loop somewhere in here, and you'll just have to search for it. All right, so I'll leave that there for you for your particular sequence. But remember, you would just take this sequence, do a dot plot, make sure that you check the find inverted repeats, and if you find two lines near the center line, all right, you compare it to itself, and you find two lines going in the opposite diagonal of the center line. So you have that center diagonal that always cuts it through. And if you find two little lines near the center line towards in the region you want, that's probably the termination signal. I tell you what, why don't we go ahead and do it? I'm just going to see if it's close. It doesn't have to be super close, but usually it is. So I'm just going to grab these right down to here, and I'll go copy C, and let's take this piece and let's put it into Eugene. So I'll go ahead and do that real quick. I wasn't going to, but why not? Let's see, and let's place this here. All right, and let's name this something like possible termination. And I'll save it as the same. Let's put that on the desktop. And I will make it a .fasta. Alright, and save that. Then let's see if we can open Eugene on this machine to do some weird things to open Eugene. Actually, I can't do it that way. I have to go. Hold on. Let's see. I have to go here. I have to go to, what is it? Opt. I think here. Eugene. And from here, I have to open a terminal. Yeah, a lot to do to get this. Find the command. There it is. Okay. Let's see if that doesn't open it. Yep, there we go. And wait for it to open. And what we want to do is we want to go over here to the dot plot, and we're going to grab off the desktop. We're going to grab, what did I call it? Termination. Potential termination or something. I thought I named it. Possible termination. There we go. Nope. Right below it. There we go. All right. And then we're going to compare it to itself. And join. Okay, next. There we go. All right, and we're going to search for inverted repeats. We'll go down to 4, and we'll make this 74%. All right, way too much. I need to reduce those parameter there. Let's make this 100. See if we see anything. Still a lot. Somewhere down in here, this looks very suspicious. All right, so let's do that again. I'm just going to have to increase the number here. Let's make it 14. Goes straight. So we'll then change the parameters to maybe 80. Nothing. Let's reduce this to 10. There we go. I bet it's these two right here. See this one here and this one here, but let's check it. Let's see if we can improve on this and get rid of some of the others. Let's increase this back to 12. Nothing when you go to 12. Interesting. It's all or nothing. Let's do 12. And let's make it 65. Wrong direction. Too much. Oops. Let's go to 75. Better. And that's looking real good right there, whatever that is. But don't know. It could be anywhere in here. It could be right there. Let's see. It's probably a little smaller than that, so let's do 8. And let's do 70. Way too busy. I'm not going in the right directions here. Okay. This looks promising, and these two. Dot pod is calculating. There we go. So let's see here. This is our termination. Let's look at what some of these letters are. Let's change this. I want to do the sequence. Not giving me all the options here. Let me see. Nope. There we go. Alright, that's too small. But GG, AG, ooh, that might be. So let's make it a little longer. This might be it. And let's make it longer and less restrictive. So let's make it 12. Makes everything go away. So we cut this back to, I don't know what, 70. Do we do this number? Yeah, I like that right there though. Yeah, that looks good. Could be it, but it could be, those are pretty long, but hey, there's some here that are together. That looks good too. See how these keep going out straight from it? So what's that sequence? That doesn't look that close. I like this down here better. I'm not real restrictive as long as you can make an argument. And of course, right here, that's enough argument for this to be a termination signature. Right here, this one, if this one matches with this one, if they look like they're going to bind together, all right. T goes to A, yes. GG goes to CC. Okay, you missed one. Then AT. You missed a few there. It could be. You'd have to go through and look, but these two look like they could form a loop. I liked these because there were several of these going out like that, and it looked like maybe they could form something like that. But either of those would have probably been acceptable as a hairpin loop. They don't need to be too far away from the center line, so kind of suspicious of these as they move further out, but they could work together to form a loop. But these two right here look really good, like they're probably, and there seems to be a center piece maybe even that might loop around. But up here, these aren't quite long enough. They might be the remember, we just took the end part, so it could be anywhere in here. This is too close. There's no, I don't think there's a, let's look at this. TT, I don't think so. These are not quite long enough, I don't think. But you could probably make an argument if you look at them and they're identical. That would be, yeah. But these two are kind of long. They're about the right distance from the center for this to be the loop. So these two look best to me. It could be something like that one. There are lots of little pieces here, but you'd have to look. Don't go too far away from the center. And you need lines about this distance, this length, at least with this length of sequence here. But that could be a termination. The termination is the one of the hardest ones to find, as far as it could be something like these. But that's kind of what you're looking for in when you search it. So you search in these sequences right along the diagonal that are going away from it in the opposite direction. All right, and you try to find the ones that will bind to one another. I don't think that. Well, I don't know. Hard to tell. That could bind to one another. But the best one would be the termination signal, probably. And it doesn't mean that there couldn't be multiple termination signals, so you may be absolutely right. But what you have to do is make a good argument. You don't have to get it right. And actually, nobody knows the real answer here. So what I'm grading you on is whether or not you make a good argument for this being your termination. Like if you chose this one and this piece, are these close enough for me to, like, here's a bunch of T's, a bunch of A's, yeah. That might be a pretty good choice right there. But you just have to make a good argument to get to credit. And let's go back to our sequence real quick. So realize we've decided that's the polyadenylation signal. The termination signal is here. And the other argument for this is termination in eukaryotes is much more difficult to predict. And there are lots of other ways besides just hairpin loops. There's no guarantee that a hairpin loop is what's needed here to cause termination. So you can always just, if you can't find one, just say, I don't think there is one. And you would be legitimate in saying that, but you would look for it after, all right, the polyadenylation signal.